Are we on? Okay, so let's get started. So let's spend a couple minutes to review what we did primarily on Friday, pipelining the CPU. I believe we left off with this exercise where we were dealing with, which one? The load redirects. Okay, so we were creating the load shadow to give ourselves time for the load data to come back from memory and write into the register file. So this is the reference solution for that lab. Okay, so your work should currently look about like this. And with the visualization, you should see at this point that your CPU is functional. We should see in the log that we're passing. We are. And if we let this CPU run, we should see it step through and iterate through 10 loops and then fall through the branch eventually. We see 2 cycles in the shadow of the loads, or shadow of the branch. So after the BLT, we have 2 cycles that are invalid. Now we loop back up. And looks like our register 14 is accumulating the sum, and 13 is our incrementer. So this is the behavior we should see at this point. And if I zip that forward, this should be the last iteration. We fall through, and everything is good. Okay, so some of the techniques that we went through, right? This is what we were trying to accomplish to create the, well, let me jump up to where we started. Okay, so we did the exercise as humans, pipelining ourselves, pipelining the CPU, and running into the hazards. We looked at work 5 with the 4-cycle configuration, representing the hazards here. And then we took a few steps to incrementally work toward the pipeline CPU. So let's see. So first, why doesn't this look right to me? Oh, so this is what we're aiming for. Right? First, we dealt with the hazards. So the branch hazard here. And the read after write hazard here. So we dealt first with, well, so this is what we're implementing first, this 3-cycle cadence that behaves like this, so that we never have to worry about the hazards. And with that cadence set up and the execution of the CPU every 3rd cycle, we went ahead and we added the logic that would deal with the hazards so that we were all ready to go to execute instructions back to back. So to add that logic, first we set up the 3-cycle cadence, made sure that the PC update was a 3-cycle loop. We did in fact partition our logic. We made the register write a 2-cycle loop just by changing the macro parameters. And we made the PC update a 3-cycle loop. So with that, we don't have to worry about the fact that the hazard cases are wrong because we're still only executing instructions every 3rd cycle. And then we dealt with the hazards. So first, the register file bypass. We added this path to take care of the 1-cycle dependence. And in the waterfall diagram, give us this path here to resolve this broken path from the register file. Then we dealt with branches by creating the branch shadow for taken branches to give us this behavior. Then we changed our valid so that we could execute instructions every third cycle now that we have logic to address the branch, to address both hazard cases. That completed the control logic for our CPU, and then we filled out the CPU to add the remaining instructions. Okay, and then we created this similar shadow for loads. So right now, you should be at this point where we have the load shadow created, meaning we have invalidated the instructions in the shadow of the load, the 2 instructions after a load. And now we can add in the memory. So first step here, if everybody's up and has their code and is ready to go, looks like it. So the first step is to assume we have the memory. We haven't instantiated it yet. The memory will give us a load data. So I think I'm having you assign the load data to 0. Maybe this just comes magically through the template. So we have load data that's a 32-bit 0 value. And when that comes back, we need to write it to the register file, right? So remember, our logic looks, our timing looks like this, right? If this is the load, we invalidate these 2 and use this timing to write the register file with the load data. Okay, so we need to add a multiplexer on the write data for the register file to either take it from the current path or to inject this load data coming back from memory. So this is what we want it to look like. We have the normal path that's currently there. We need to hook up the data coming back through a mux, which is 2 cycles ahead in the pipeline. We also are going to use the load store. For loads and stores, we're going to use the ALU's result as our address. So let's see, step 1 here is for loads and stores, which are identified as isLoad and isS-inster. We want to compute the same result that we do for add-I. That's the computation that gives us the, the address, right? So for loads and stores, the address is one of the source registers. I forget. It must be source 1 plus the immediate value, right? And that's the same as add-I. So first step here is to update your execution unit, your ALU, to perform that operation for loads and stores. And then this other path to load or to write the register file with the load data coming back. Okay, so that means you need to look ahead in the pipeline too to grab the associated load data. It also means you need to know where to write into the register file and whether that write is valid. So think through the control logic to perform that write operation for the load instruction 2 cycles late. Okay. Any questions about the lab? So I'll walk through just the first part. So the first part is hooking up or controlling the ALU to perform add of source 1 plus immediate for loads and stores. And that's going to give us our load or store address. So I'll scroll down to my ALU. There it is. And add I is where. So if we're add I, or we're a load, or forget the name of the signal. What is it? Is as inster. And I don't know why they're saved issues. Then we want to compute source 1 plus immediate. Okay, so that's it for that one. I'll give you a couple more minutes to work on the second step. So to hopefully clarify some confusion that a couple folks seem to have around why we're doing step 1, right? Why are we using the ALU like an add-I? For the loads and stores, we need an address that's computed as a base register, a base address that comes from a register, and an offset that comes from the immediate of the instruction. So another way that we could implement this logic for loads and stores, right? We want to compute the address for a load or a store. The computation that we want to do for a load or store to get the address is the source 1 register value plus the immediate offset, right? That's the definition of the load or store instructions address. So if we look here at the definition of load and store, right? This is the address, RS1 plus the immediate. So we could have a separate expression, source 1 value plus immediate is the address, and then we use this address to feed into the memory. All we're doing in step 1 here is we're trying to avoid some redundant hardware, right? We already have a computation that's doing source 1 value plus immediate. We do that for add-I, right? So instead of doing a separate computation, load and store don't produce a result. Load and store do not need to write the register file like other operations, right? Store has no destination register, and load, we have to go out to memory to get its destination register value. So the normal path of writing the register file is not used for either of those instructions. So we're not using the result computation from the ALU. We may as well just use the ALU to do the computation of the address, okay? So the more direct implementation of the definition of the instruction set is to do a separate expression. We're just saving some hardware and, using the ALU when we are a load or a store to do that computation for us. Okay. So let's look at step 2 of our lab. So step 2 is that the memory is going to return the load data a little bit late. We need to inject that into the register file. So implementing this mux here. So that mux is feeding into the register file for write. So here's register file write. We need to modify. First, I'll look at the data going into the register file. So here's the data. We were directly feeding the result of the ALU into the register file. Now we have to inject this mux and select that based on whether we have a load instruction. So, and not just whether we have a load instruction, but whether 2 cycles ago we had a load instruction, right? Because we're doing the injection 2 cycles late. So if is load and 2 cycles ago, then we want to write the load data also 2 cycles ahead in the pipeline. Otherwise, we want our default behavior. So in the case of load, we have created the shadow. So the instruction 2 cycles later is not trying to do anything else. We'll use that time to inject the load data. So again, looking at our waterfall pipeline diagram, right? This guy is the load. We squash these two and inject that load data delayed by 2 cycles. So the data that we're writing to the register file is from stage 5. We have the mux in stage 3. We need to look ahead to. So that's the data, but all we're doing is presenting data to the register file. We have to tell it to actually do the operation. So we also have to enable it. We can, I guess just to keep things consistent, we'll use a ternary again. So I don't think our isLoad signal factors in validity. I don't remember for sure, but let's keep valid separate. Actually, no. Let me check that. Let's look at isLoad. So we do want to make sure that we're only doing the injection for a valid load instruction. And I don't see valid factored in, so valid load. All right, so I guess we have this valid load signal. Let's use that. Okay, so setting up the data, it doesn't really matter whether we factor in validity or not. Validity will determine whether we use the data, but what we set up doesn't matter. But just to be consistent, let's only do it for valids. And we'll do the same thing here. So look ahead 2, and if we're a valid load, then we want to write. So 1 tick B1. Otherwise, we'll do the expression we used to do. And also, for the right index, same thing. If we had a valid load, we want to use its index, right? So what is the load's index? It's the RD for the load, right? So if we have a valid load, we want to use its load, which was, is 2 cycles ahead now in the pipeline. Otherwise, we want to use the load, the destination register for the instruction itself. Okay, so that's step 2. Are there any questions about the logic? Yeah. Sure. So if we, let's say during reset, for some random reason, we haven't really thought about what's happening during reset. It could be that during reset, we're getting random values of our instruction signal. That might get interpreted during reset as a load. So that would be a load, but not a valid one. We wouldn't want that instruction to have an impact on the register file, right? We only want valid load instructions to have any impact. So, just like always, anytime we're updating architectural state, the register file is architectural state. We need to be careful to only do that for valid operations. That way, invalids can be anything. You can approach that different ways, right? I mean, one way to approach invalid instructions is to sort of, once you figure out it's invalid, inject something into all the signals that makes that instruction look like a no-op instruction that would do nothing. That tends to be expensive. You have to inject into a lot of signals. You might have to change opcode values or the entire instruction depending where you figured that out. It's much less impact physically to the logic if you are careful about the control logic and use things like valid signals. So yeah, so we factor valid into isLoad so that we can only impact, have this impact for valid instructions, valid loads. Any other questions about the logic? Okay, so it's here and here. So now that we have all the control logic in place, let's actually instantiate the memory. The next lab here, similar to what we did with the register file, just uncomment the macro. It's all here for you. The macro, once it's uncommented, is going to give you these signals. So let's look at this. The memory, it's a small toy memory. It's just 8 entries. And of course, they're 32 bits wide. We're implementing a word memory, supporting only the word load and word stores. We need to reset the memory so that we can clear it out to 0. And the memory needs to support either a load or a store each cycle. So either a read or a write. This would be termed a one read/write memory. Okay. So there's signals for the write. We've got a write enable and the write data and the write address. Right? So the address is used for both writes and reads, loads and stores. And the write enable and the write data, and then on the read side we're using the same address input and a read enable. And for reads or loads, same thing, we have data coming back. So we have read data, which becomes our load data. So hooking this up and giving the signals names that make sense in the context of a CPU, right? Let's see, connect interface signals above. Okay, so this is connect all the signals, right? So this guy coming out is our load data. We'll give that a name that makes sense. So you can assign that to load data. We've got our address that we computed in the ALU. So that's our result coming out of the ALU that we use for our address. And the store data is coming from source register 2. Okay, just looking at the definition of the store instruction. I don't know if I had that in the slide. So store instruction has a source operand RS2 that provides the data that you're going to write. Okay. So the store data is coming from here. You want to make sure that you're getting that after this mux, right, in case it was the previous instruction that wrote that register that's providing the store address. You know, if it was, that value is coming through this bypass path through the mux. And then, you know, think through what's needed for the read enable and write enable. right, should we talk this one through? So let's delete DMEM. I'm going to compile just to see what we get. It looks like we get a bunch of confusing messages. Yes, we do. Oh, no, these aren't so bad. Okay, so focusing on the messages from Sandpiper first. You know, they're a little bit confusing because this is an error coming from a line of code that you didn't write. This is the template infrastructure that's hooking things up to support the visualization using features I haven't taught you. But, you know, I think you've all seen errors similar to this at this point. You can get a hint, at least here, from the DMEM address. So we see it's used but never assigned. DMEM read enable is used but never assigned. So these are all the interface signals of the module that we just, or the macro that we just instantiated. So let's hook them up appropriately. Let's do our memory here, I guess. So reset already exists. That's already hooked up just naturally by name. Let's look at DMEM write enable. We'll just do these in order. So when do we want to enable write to the memory? We want the write to happen when we have a store operation. So that's going to be our is inster, I believe it's called. And what about validity? So we're going to want to make sure we don't write the memory for invalid store instructions, right? So let's factor valid in here. I don't remember if I have a valid store. I don't believe I do. So let's do it that way. What's next? DMEM address. And that, again, this is an 8-entry memory, so 3 address bits. It's a word memory, not a byte memory, whereas the DMEM, whereas the address that's coming out of our ALU is a byte memory. So the address is coming out of our ALU, right? We used our ALU to compute the address in the earlier lab. So result is our address, and since we're hooking up to a memory that's very small, it's only 8 addresses. We only need a few bits of address from our result. Since result is a byte address, we're going to ignore the lower 2 bits, which are within a word, and just look at the word address and only 3 bits of it, right? So that means we just need those 3 word address bits, which are going to be 4 to 2. Anything above that, we're going to ignore, which means if there are, if they are non-zero, they're going to alias to the address bits that we're using. We could also check to make sure they're not, make sure they're 0, and if they're not, don't write, so that we're not aliasing different addresses into this small memory range. I'm just going to assume that we have a memory or we have a program that's utilizing only the memory that it has, and just directly hook it up like that. Before I move on, any questions about that hookup? So the next one is the DMEM write data. That one's 32 bits wide. And so what's the data that we're writing? We're writing when we do store operations. And the data that we're writing, based on the definition of the store instruction, is the RS2 data. So I think that was source to value, if I remember right. And then the read enable. So reads are loads. So we're doing a read when we have a valid load instruction. Okay. So that's our inputs, and then our outputs. Only one, DMEM read data. Sorry. Is load data, there we go, which is going to be 32 bits. Should be hooked up to the read data. How'd I do? Should I compile? Let's see what we get. Okay, I didn't do too well. Let's see what we get. So is s inst inster, I believe. I don't know why I got inst. Ah, okay. So that explains one of the students' issues. I think that was a typo as well. I should have checked my log. And let's see what else. DMEM read data is used earlier than it's assigned. So what I want to implement is this picture. The memory is in stage 4. All of my inputs are ready in stage 3. So assigning the inputs in stage 3 is fine. But my output from the memory is apparently not available in stage 3, which from this diagram makes sense. So let's move this to stage 4. So load data is assigned but never used. Load, that's because I spelled it wrong. Okay, log is clean. Our simulation passes. We don't have any load instructions to actually test this behavior or store instructions. So we'll look at that next. But at least at this point, I didn't break anything for the test program. Yep. You're looking where? Mm-hmm. No, that would be different, right? We want, so all of these signals related to the load, related to memory, the instruction is going to get sent to memory and the associated load data is going to come back all in this pipeline. So yes, the memory returns the load data a cycle later, but it's going to be associated with the stage that's one ahead, right? If we use so, I mean, in part, your question depends how the memory was created, but it was created to kind of fit in this pipeline. So the load data is naturally associated with the instruction that's doing the load, or I should say the DMEM read data is associated, you know, corresponding to the inputs in terms of their stage. Okay, so when we do the assignment of load data to DMEM read data in stage 4, right, we're right at the output here, we want to keep that association. If we were to look, so you're suggesting that this remained 3, but we do ahead by 1, right? So if we were to do that, we would be doing an assignment of load data at 3 to the DMEM read data at 4. So the timing association of the load data that we hooked up is different. So then when we recirculate that into the register file, you know, the recirculation into the register file, right, is looking 2 cycles ahead in the pipeline for the load data at stage 5. You're going to get different staging of that data, right? If we were to assign that as an add 3, that would get staged an additional 2 cycles. It really is associated with add 4. It should be staged just 1 cycle. Okay, so the, you know, bucketing the logic to a stage is not the same thing as looking ahead or behind. You should look at these ahead by or behind by as with respect to the transaction, right? We have instructions in the pipeline that are marching through. When you're referencing ahead in the pipeline by 1, you're referencing the instruction that's ahead of you by 1. And likewise for behind. Whereas the stages is just a question of when you're performing computations, right? So anytime you change the relative reference, the ahead by, behind by, that's going to change functionality. Anytime you change the ats, that's going to preserve functionality. And the functionality here, right, if we just simplify this, right, glom everything all into 1 cycle, imagine the load happens instantaneously within the cycle. Everything is in that 1 cycle. We're not looking ahead, we're not looking behind. So the fact that we had to move this to stage 4 is just a fact that we laid out the pipeline differently. We want the same functionality. So that's kind of a key. I want the same functionality, then I should only be changing the ats. This ahead by 1 would be a logical change. We'd actually be looking at the instruction that is ahead of us, which is not what we want to do. This is all related to that load instruction. Right. That explanation was a bit scattered, but hopefully it helped. So this is 4. And you know, with all that kind of stuff, you can play around with the smaller examples and you know, take your cues from the logic diagram, see where flip-flops are implied. But at this point, we should be passing, producing 45. Looks good. Any other questions about that? So the next lab is to test this a little bit, not very exhaustively, but at least let's do 1 load and 1 store instruction. So go ahead and add a load and store instruction into your program. We'll just take the value that's in X10, which is coming from this add, right? So we do our last branch, we fall through. I think the value, yeah, the final result at this point is in this point being the BLT instruction. Our result at this point is in X14. So this last add is just moving the value from X14 into X10. And then we'll add these load and store instructions that are storing X10 and then loading that same value into X15. Right? And then you can change the test bench then to test that the correct value now is in X15, not X10, to test the load and store. Okay. And I suppose we can walk through this one together. It's not rocket science. my load and store, and then changing my mini test bench, which is here, to check register 15. So perhaps I picked up some funky characters when I cut and pasted. I'm going to re-enter all those spaces. I think I added a space here, which matters. I took away spaces. Okay, and of course, if it's not passing for you, you may have made a mistake in the past 2 labs that you have to debug. All right, so let's get started up again. I did find a bug in my own code, actually two bugs. So in case you guys inherited those bugs from me, let's take a look at those. So it looks like the logic that I coded up for instruction fields, for validity of the fields, it seems like all of them are just a copy of the first. I don't know what happened. But so let's take a look again at this table, which tells us which instructions have which fields. So R-type has all the source registers. Actually, let's do it the other way. So which ones have funct3? All but U and J, which I'm not decoding. Okay. And RD does not exist for S-type and B-type. So this is wrong for me. Should be like that. And RS1 is everybody. RS2 is not I-type. So RS2 should not have that term. What else? RD, RS2, func3. Okay, I think that's everybody. Yeah. Okay. Okay, so before I compiled that, I saw there was a valid destination register here for the store instruction. That's how I noticed the bug. And I was writing to a register that store should not write to. The other bug that we noticed, and let me confirm this, the store instruction and the load word instruction should have an RS, so store should have an RS1 of 10, RS2 of 0. They're backwards here, so I think this is an issue in the assembler. Should result in bad behavior. Let's see what's happening. X10 should be the address. Okay, so I think the assembler is sort of consistent. Oh, why does that work? In any case, somehow source 1 and source 2 are flipped around. If you're following the instructions in the course, it works. Seems to anyway. But just be aware when you're looking at these instructions that things are flipped. Any questions about what we've done so far before we move on to jumps? Okay, so let's go to the slides. Okay, so jumps are much like branches. Yeah. Yeah. Yep. Well, okay, 1 minute. Maybe I still have this logic wrong. Let's take another look. Is UJ, okay. So J and U type should have a destination. And that's it, right? Does that look right? Okay, and that's going to be important for implementing jumps. Okay, so for jumps, so jumps are like branches, except they're unconditional. The terms branch and jump are not used consistently by different instruction set architectures. Sometimes jumps are defined to be absolute, going to an absolute address, whereas branches are relative. In RISC-V, the distinction is whether they're conditional or not. So branches are conditional and jumps are unconditional. Both are relative to, actually, is that true always? Yeah, I guess it is. So both are relative to a base address. Jump and link is relative to the PC, just like branches. Jump and link register is different from the branches in that the base address is given by a source register, source 1. Okay. So let's see. So jump and link looks just like a branch except no condition. And jump and link is going to be different. So first thing we'll do is define this is jump. To decode, are we a JAL or a JAL-R? And just like we did for taken branches, we will address the control hazard, meaning the update to the program counter and the dependency on the following instructions, by creating 2 invalid cycles after the jump, right? So we have the same picture we had before. Let me just go up to that, wherever that was. Somewhere back here. I guess we'll look at this one. So just like we had for branches, we have this control hazard, right? Where in the case of branches, we need to know whether we were taken or not in order to know the proper target PC. In the case of jumps, there's no comparison. So potentially, we could do this path a little earlier, right? We can do the offset calculation in the stage before. Potentially, we could drive that offset calculation to the PC mux. We already know that whether we're a jump or not. We're not going to do that optimization. We'll just do it the same way that we did branches. If you'd like to try that optimization, feel free. Maybe I shouldn't say optimization. It's not a logic optimization. It's a performance optimization, right? But we'll treat it the same way with a 2-cycle delay to get the target. So we're implementing this picture, right? So for jumps, just like branches that are taken, we need to create these 2 dead cycles, the shadow of the jump. So that's the first, that's step 1. Since JLR, jump and link register, so first of all, just terminology. The link register is the register that determines where you need to jump back to if the jump is a function call, right? So we're going to use jump and link register or jump, what is it? JAL, jump and link. The link part is storing the PC of the jump so that you remember where to call back to return back to, rather. Right, so these instructions would be used for a call. I think they'd also be used for the return, but the link register is important for the call. So the behavior of JAL and JAR, their destination register gets the value of the PC. I thought that should be in here somewhere. I don't know why I didn't have that. So that's... So I guess, you know, we defined that earlier, so let me jump back here just to explain the behavior of jumps. Right, so here's the destination register for JAL, jump and link register. The register part says that the address we're jumping to, the base address, is coming from a register versus coming from the PC. In either case, we want to link the program counter for the return. So in either case, we write the destination register with the PC of the jump +4. That's the return address. So when the function that we're calling does a return, it has that return address. We saw that when we looked at the assembly coding, right? Let's see. So let's go back to this picture. All right, so when we do a function call, we need to store away this return address so the called function knows where to return. So this return is a pseudo-op that implicitly uses the return address register as its target. Likewise, the call instruction is a pseudo-op that implicitly writes the return address, the return address register to remember where to return to. So this call is writing return address. This code is storing return address in the stack so it can hold on to it associated with the function. And then when this function returns, it's going to load the return address into RA, and that will be the target of the return instruction. So, okay, so let's go back to our jump. Okay, so the behavior that we need to implement, we already have the destination register written with the correct value, the PC +4. But to add support for the jump, we need to, step 1, create that jump shadow, just like the branch taken shadow. And we need to compute the target of the jump. So for jump and link, that's the PC plus the immediate, which is the same calculation that we do for branch. So that calculation we already do. We need to add this calculation for source 1 plus immediate. Okay, for JALR. So you'll compute this JALR target PC. We have branch target PC, and you can update the expression. Let's see, to select create PC. Yeah, so you already have this expression for the branch target PC. We can use that for JAL. So step 2, add in this adder, and then step 3, is to use that in the PCMux. So the PCMux currently has the case for take and branch, which uses this target. We also want to use this target for JAL instructions. And then for JALR instructions, you want to use the new calculation that we just did, this JAL target PC, this adder. Okay, sorry, I was jumping around a little bit, but is that all clear, the behavior of jump and what we need to implement? Okay. let's step this one through. Okay, so one step at a time here. So the first step is to define isJump. So let's go up to where we do our decode of the instructions. That's here. So we'll also define isJump if is JALR or is JAL. And we have to create invalid cycles. So let's see, where do we create the invalid cycles for branch? So we generate a valid here. This is where we're computing our branch shadows, right? If we're a taken branch, we create the shadow. If we're a load, we create the shadow. We want to do that also if we're a jump. So if the last instruction, what did I just call that? Is jump, I think. Yeah. If the last instruction was a jump, or the instruction 2 instructions ago was a jump, then we also want to create this branch shadow and force valid to low. Any questions about that? So that should be step 1. And then we'll compute the JALR target PC. So let's do that. So in the diagram, I put that in at 3. That's going to be, okay, so I have to do that after I have my source 1 value. So we'll do that in R3 where we do the comparisons for the branch taken. That's here. So I'll just put that right here. So JALR target PC, and that's going to be a 32-bit value, is going to be the source 1 value plus the immediate. Any questions about that? And then step 3, we want to update the PC mux to properly use the jump target. So branch target PC computation we're going to use for jump and link. Yep. So we'll select this case also for, why is that? Oh, that's my cursor. So if the instruction ahead by 3 is jump and link, then we also want to select the branch target PC. And we need to add a case now for jump and link register. So we only want to do this if we are valid. So I'm going to, actually I need to consider that here as well. Again, we don't want to mangle the PC for an instruction that's not valid. Defaults. So I guess if we're not, yeah, actually if we're not valid, it shouldn't actually matter. We should be correcting the PC for any situations that put us in a branch shadow. So let's be daring and not worry about that. All right, and then add the case for is JALR. And we just created the JAL target, so BR, JALR rather, target PC. All right, so if we had a jump in length, 3 cycles later, we want to use its target PC. Did I get that right? You guys have too much faith in me. All right, let's compile and see what we get. Looks like we're still passing. Of course, we haven't added any jump instructions. So if you would like, you can play around by adding jump instructions and testing them out. We're doing very minimal testing here. At this point, if your CPU is passing, call it good. So in case folks have more bugs to resolve, I'd say we take another 15 minutes. If your cores seem to be working, you can use these 15 minutes to do additional testing. So add some jumps to your program, test the behavior, see if you can uncover some more bugs, and refine your core more. But you know, other than debugging, good job. In roughly a week, you made a RISC-V CPU, and this is the fact that we're able to do this class and get folks designing a RISC-V core in a week is raising a lot of eyebrows and getting a lot of attention. It's quite an accomplishment. This content, generally it's Intro to Digital Logic, which is a full course. It's computer organization. It's maybe an FPGA lab. And you've gone through all of that essentially in a week. Of course, there are more topics you could get into, right? Often those courses might go into things like branch prediction, other things, do a deeper dive on, say how logic synthesis works. But you've certainly covered a lot more ground than is typically covered in a week. And so good job. So I'll give you 15 minutes just to play around, debug, and then we're going to switch gears and do more lecture style content about the nature of design teams and put this all in the context of real world of industry, how industrial teams go through this kind of exercise. So yeah, this actually looks wrong in my code too. So I have this is jump signal, which is not factoring in whether the jump is valid. So that probably can result in bugs where we have a jump that's in some other shadow, it's invalid. It creates its own shadow, right, which it shouldn't do. So we really should be factoring valid in here somewhere. I think, so let me see where else I use this. I think we'll just factor valid into is jump. That's it. So let me make a valid jump signal instead. I think my instructions in the slides are slightly different, but and we don't actually know whether we're valid at this point. So let's move that to here. Okay. Let me see if I need to update anything in the slides here. I guess we have. Since we have lunch break coming up in about 20 minutes, I'll just let you work on this for 20 minutes. We'll start the new topic after lunch. makes a good break. So again, if you have your cores seem to be working, play around with the instructions, do additional testing. You know, we have a lot about the core that we never tested. We're only running our test program that has just a handful of instructions. You can, you know, there's 40 or so instructions in the architecture that you can test. I think I have one or two just sort of wrap-up slides that I can cover before lunch. So you essentially built the RISC-V RV32I, the base instruction set, right? But we did take a couple shortcuts. So the things that we didn't actually build, the RISC-V core or RISC-V instruction set architecture defines some control and status registers. This is very typical of every instruction set architecture. They are exactly what they say they are. They either report status about the CPU or they control the CPU in some way. So for the base RISC-V instruction set, these are things like cycle count, time, absolute time, wall clock time, and instruction count. These are status registers. Okay, so also a couple oddball instructions that we didn't support since we don't have control and status registers. We don't have to define the instructions that operate specifically on control and status registers. So there are instructions that read and write those registers. There's, well, these instructions called e-break, e-call, and fence. Fence has to do with memory consistency. If you have a multi-core system where you have many CPUs all sharing the same memory, we don't have to worry about fence. We didn't even bother to interpret the instruction. E-call and e-break have to do with exception handling. I don't actually know the details of them. We also didn't support byte granular memory, as we've talked about before. We implemented a separate instruction memory and data memory. The instruction set architecture defines a unified memory. When you actually implement a CPU, what you would generally do is you have a unified memory that contains both instruction and data. And then closer to the CPU, you have small caches that keep local copies of the data from memory for fast operation. And generally, the first level of caches would be separate between the instruction and the data. So what we implemented is more like the two caches, and you know, there'd be a whole data hierarchy underneath that with the actual memory. We also shrunk down the register file. That's just a parameter, and the only reason I did that is so that we can fit these designs more easily onto tiny tape out if anybody is intending to do that. We also didn't implement the privileged architecture. So when you boot the CPU, you power it on, it's going to go through a boot sequence, standard, you know, processing to bring the CPU up into a stable state, right? So you've got the reset signal that powers up the hardware into a stable state. You also have to initialize the memory image into a consistent state. You have to work with the operating system to do that, to boot everything properly. There will be some, you know, on the actual system, there will be some flash memory that contains some privileged code that the user should not be able to muck with. And you need to be able to safely get that privileged code onto the CPU to work with the operating system again, to sort of provide proper protections to make sure the user code doesn't mess with things that it shouldn't be able to mess with. And so, you know, there's a whole architecture around that boot process that we ignored completely. And a privileged architecture that defines especially control and status registers to provide that protection, the different modes that the machine can be in. So when you power up, you're going to be in a privileged mode. And there are exceptions and traps and interrupts and you know, basically when user code does something bad, and privileged code needs to deal with it, you know, there's a whole architecture that defines how that happens. So the mechanisms to enable that handoff between the user code and the privileged code, we didn't worry about. So all of these things that are missing, you know, potential project ideas, right? You could add these capabilities into the CPU if they're things that particularly interest you. So along this journey of building the CPU core, you learned fundamentals about digital logic, you learned CPU microarchitecture, you learned about RISC-V, which is, you know, sort of making very rapid waves. I guess maybe it's in its 12th year or something like that. And for the level of adoption that RISC-V has gotten over 12 years, it's rather phenomenal. You learn transaction level Verilog and microchip, my technology, you know, we use the tiny tape out flow, which is all built on open source tools. So the fact that we can now use an entire open source tool stack to implement an ASIC is a rather remarkable thing that is new to the industry, and really opens up opportunities for academia to collaborate where it was sort of shut out before by the proprietary nature of all these tools. I think that's my last slide going into, well, okay, so the next thing actually is to play around with this in silicon. So if you are, I forgot I had this in the plans, but if you are comfortable with your CPU at this point, before lunch, or yeah, I'll say before lunch, you can again go through these instructions. So again, these are linked from the course repository. Same process as before, which we did with the calculator. Also, if you want to try your calculators now with the debouncing enabled, you can try that. Just check with me to make sure you have the right update. But the CPU, fortunately, is entirely driven by your program. So there's no special hookup for inputs for the CPU. It should be, if you were working in the template as intended, that actually we can verify this in this visualization. So there's no inputs to worry about. That's all embedded in the memory. The output, our CPU has the passed and failed signal that we use to communicate with microchips, so it should be that those are hooked up to the outputs of the FPGA. So I believe passed and failed are hooked up to bits 0 and 1, which would be these two LEDs. I think this one's passed and this one's failed. It should be, if we jump back earlier, that's not set, and then going forward, it reports passed. So I think that's hooked up correctly. Make sure that's the case. When you actually build this for the FPGA and run it on the FPGA, you're just going to see passed or failed, right? That's the extent of our hookup right now. But you can certainly try that exercise. And this design will fit on the FPGA. Right? And then when we come back after lunch, we'll start into the next module. You see the code for which? This one.